So this is going to be the start of a series that is primarily concerned with the application of machines to solve or compute particular problems. And in order to begin talking about machines, we have to begin with kind of a general classical description of the universe, which is the strong form. So we can define some physical body that is a subset of Euclidean space in d dimensions. And what we're going to do is prescribe a particular solution to this region, which is called the Laplacian. And this is a strong statement about a particular region that we are trying to classically describe. This is what we'll call the strong form. And what this means is that every single mathematical point, just say, some point x, assuming this is a continuous physical body, or it could represent, anything from, a metal or heat conducting or some elastic rubber band, anything, something that's under stress. It demands that at every single mathematical point, the Laplacian of our field balances this external force that's applied to this region of space. And this is kind of mathematically arrogant because let's say we have some f of x here that describes, a heat source, if you will. All right? Well, what we're assuming about this region is that the u here is going to be a smooth, twice differentiable function over this domain, over this entire domain. And it's going to be defined this way perfectly. But, if we were to try to compute this with, a finite amount of bits, that's not really, possible to do. We can't solve the strong form. Even like for more physical problems too, if you have a crack in the material or some point load, right, that I said here, this is the heat source, is a point. Obviously, the derivative is going to explode there, and so the strong form will fail. Now, what we need to do is talk about, again, let's formalize the strong form, which is just simply a piecewise statement about this domain, which is that if we have the Laplacian, which is a function of, some position that's balancing the force in the domain, and also another part of the statement is that this will equal 0 at the boundary. Okay, so we're assuming here that everything, the strong form here, is being satisfied, continuously for every single point, and that the function will be equal to 0 at the boundary. Okay, or in other words, we're like grounding it or clamping the rubber band so that it won't be able to. It's strict. Okay, we're strictly confining this boundary condition, which is called the Dirichlet type. Now, what we need to do instead is relax this assumption about the world. We'll never be able to compute anything by doing this. So instead of enforcing this equality at every single point, right, what we can do is enforce on average or in energy. And we can introduce something called the observer test function, right? Or let's do another color. Let's see. That's not what I wanted to do. Okay. And this test function here is going to be also defined to go to 0 at the boundary. But you can think of this as like a virtual displacement, or like a virtual kind of way that we are, trying to survey this region. And this constraint here is critical because it'll allow us to define a weighted residual such that if we were to take the integral of the product of this strong form, we can then get an integral equation, which is a weak form, that convolves the sources with the test function and equates that to essentially this. So you can think of V as this virtual particle, or this virtual probe. And what this will allow us to do is multiply the equation, again, by V, and integrate over this whole volume on both sides. And the magic will happen when we try to integrate, okay? So if we want to integrate this particular term by parts, what we can do is say that this integral is equivalent by invoking Green's first identity, or just the integral by parts for vector calculus. We will get a boundary term and a volume term. But again, what did we constrain here? We constrained that the boundary was going to go to 0 for this particular function. It's just going to become 0 at the boundary, and so we don't really care about this part. We're more so concerned with this, okay? And so again, you can think of this virtual probe, and after integrating through the whole volume, this allows us to magically, shift one derivative from u onto this derivative here from u onto v, or this gradient. And this will then be integration by parts in higher dimensions, because we will lower the requirement on u and raise the requirement on v, and they will meet in the middle and have this kind of consensus here. Okay? And what this allows us to do is then reason through this physically, right? Since v is going to 0 on the boundary, and again, v is going to 0 at the boundary flux term will vanish. So this has like a physical meaning. All right? Now, what happens next is we will arrive at the weak form. Okay? We can define the weak form. Which is essentially just the fact that we now have this new kind of bilinear expression, and this left side of the equation here, we can call it just a of uv, okay, assuming that boundary term vanishes. And this right side, we can call it L of v, right? It's not really, the sources are given, okay? But the forcing terms are given, that this Poisson equation is, this Laplacian is balancing, okay? Now, and assume, again, this is a system that is in equilibrium, right? This is why Poisson's equation is taught in electrostatics, because it describes a particular equilibrium. Now, you can think of this term here as kind of like a straining. Or you can think of this as like just internal. Let's think of another way to say this. Just internal energy change when probed with V. So this is telling you, this bilinear map is telling you the energy change when probed with V. And we're saying that this must, in equilibrium, this must be completed, or this must be equivalent to the work done by external forces during that probe. If this balance here, this A is equal to L, if it holds for every possible probe, then this system is said to be in equilibrium. And the equation, this gives us a new equation that a machine can actually solve. Because it doesn't look for smoothness, it's actually going to look for the state where the energy budget balances perfectly, right? And so we can formally say that this is a variational problem that says find the function u, the function being described by the Poisson equation, such that it is a member of a Sobelev space, which has Dirichlet boundary conditions, such that A of u and V is equal to L for all test functions that exist that are defined over that Sobelev space. And again, why is this machine ready? Why can we solve this with the machine? Is because we only need the first derivative. We only need nabla u. Okay? And we don't need the second derivative here, which is the Laplacian in general for Euclidean space. All right? Also, if you remember, Sobelev space has this unique property of being, if u is a member of a Sobelev space in general, okay, not really specifying anything about the boundaries, this means, or let's just say this implies, that it is square integrable. In other words, the integral of the square of its gradient is finite. And so what this also, the Sobelev space has physical meaning because it says that it has finite energy if we were to integrate over all of u. Also, another important quality that we are interested in is symmetry, which is that if we have our bilinear form here, we can also interchange it, because that's just a particular constriction or a constraint that we will be using in the weak form. This leads to symmetric matrices later. So we would get, some A to be equal to its transpose, which then allows us to diagonalize and solve linear equations. So this is why the weak form is the way that we must solve differential equations. Okay? So now I'm going to stop here. Okay?